In this example, we're going to talk about a particle's actual position. So in the last two examples, we could find the particles or the object's displacement and the total distance traveled. But what if we said, well, okay, given this velocity function or the velocity graph, where is this object? Where is this particle at, for example, t equals 7 seconds? In order to find that, we need an initial condition so that we can actually find the particle's position function. So, what I mean by initial condition is we need to know at what time, and we need to know at a certain time, where is the particle. So in this example, a particle moves in a straight line with this velocity, meters per second, where t is time in seconds. At t equals 2, the particle's distance from the starting point is 8 meters in the positive direction. This is our initial condition. This says, we'll call our position function s. S of 2 times 2. This particle is 8 meters away from the starting point. So, now that we know that, we can find the position function, and therefore we can find out where the particle is at any position, but specifically at t equals 7. So, particle's velocity is, let me give myself a little bit more room here. So particle's velocity is v of t equals 3t root of 3t minus 2. Okay, now remember that the position function is going to be the integral of the velocity function. So s of t equals the integral of, I'm going to rewrite this to be 3t minus 2 to the 1/2 power dt. Now let's integrate this. S of t is going to equal 3/2 3t minus 2. Oh, excuse me, to the 3/2. Just joking, this should be 2/3. All right, plus c, because this was an indefinite integral. And this is where our initial condition comes into play. We're going to use that to solve for c, and then we have a position graph, or excuse me, a position function. So s of 2 equals 8, which means if we plug in 2 for every t, that's going to equal 8. So 8 equals 2/3, 3 times 2, plugging in 2 for t, minus 2 to the 3/2 plus c. So I'll keep writing down here, 8 equals 2/3. 3 times 2 is 6, minus 2 is 4, to the 3/2 plus c. All right, let's simplify this more. So this 4 to the 3/2, that's like saying 4 cubed and then the square root of that. Or we can say square root of 4 cubed. That's where this over 2 comes from. So square root of 4 is 2. Here, I'll write this out. 8 equals 2/3. Or I suppose you could use a calculator. Anyways, so square root of 4 is 2. 2 cubed is 8. So when we simplify this, we get, okay, so this is going to equal 16 over 3 plus c equals 8, which is 24 over 3, which means c equals 8 over 3, because that's 24 over 3 minus 16 over 3. Now, our position function, s of t, equals 2/3 3t minus 2 to the 3/2 plus our constant, which we found out was 8/3. Now, if we want to know the particle's position at t equals 7, we find s of 7. We plug in 7 for every t, And when you simplify that, you end up with approximately 57.88 meters, which is about where the particle's position is at t equals 7 seconds. So remember, just to get that, you plug in 7 for t and simplify. So you end up with 21 minus, so 19 to the 3 halves times 2/3 plus 8/3. And that is how you use an initial condition to create a position function given a velocity function.